Now we define resistivity. So resistivity is rho. It is defined as 1 over sigma. The sigma is the same which comes from Ohm's law. Now since resistance is given as L over sigma times A, you can rewrite resistance as the resistivity rho times L over A. So instead of 1 by sigma, you are writing rho. So the important consequence of this formula is, you can see if the area goes up, the resistance goes down. So resistance will go down if the area goes up. Now if the length goes up, the resistance will also go up. Now we talk about deriving Ohm's law. Now we know the formula that V is equal to U plus AT. So this is from kinematics. Now V is the final velocity. This is the velocity after you have applied the electric field. And U is the initial velocity. So this is the velocity of the charge carriers before you apply the electric field. Now before electric field is applied, the electrons or charge carriers move randomly. So electrons or charge carriers move randomly. So the average velocity here would be 0. So you take the velocity over all the charge carriers, it will be 0. They're just moving randomly. So net displacement could be 0. Now after electric field is applied, these charge carriers or electrons are still moving randomly, but they also start moving because of the application of electric field. The charged particles start drifting. So they start drifting in a particular direction. So say you can see that there is a charged particle. It is moving in blue. So it is still moving randomly, but it is trying to go towards one direction. So this is Vd vector is the velocity. So you just see the displacement and the time. So Vd vector, this you take average over all particles, you write V average. This is equal to U average plus A vector dot T. Now U average is 0, this we have discussed before. So you get the formula as Vd vector is equal to A vector dot T, where T is the time. So standard kinematic equation we have used. So the Newton's second law states that force is equal to mass times acceleration. And the force is given to us as Q times the electric field. So this is the force in electrostatics. So acceleration becomes Q E vector over M. Now if the charge carrier is an electron, then Q is just basic charge E and M is the mass of electron, M subscript E. So this acceleration becomes E over ME. So E vector is the electric field. So Vd vector becomes A vector dot T. So this becomes small e capital E divided by mass of electron times the time. Now this we want to plug in into the current density. So J is the current density. J is equal to I over A. So I is NEAVD. So this we discovered before. And you divide this by A, you get NEVD. So now we will plug in the VD here. So first you notice that this current I is not a vector. So the VD we plug in here is not velocity, but as a scalar. So you just enter the magnitude of VD vector. So if you enter magnitude of VD, you will have to take the vector sign of the electric field also. So you get J is equal to NE times E times capital E divided by mass of electron into time. So J becomes NE square times T divided by mass of electron, this entire thing times the electric field. So we denote this quantity in the bracket as sigma. So this we call as sigma, and this is independent of the electric field. Now sigma is the conductivity. Notice it is independent of the electric field, and we have been able to derive Ohm's law.